In Chapter 2, we took a look at gravity. But when we were talking about gravity, it was actually a simplification of Newton's law of universal gravitation. And Newton's law of universal gravitation states that any two objects in the universe that have mass will be attracted to each other. So I want you to think about this for a moment. You have a mass, and you are in the universe. And your pencil beside you has a mass, and it is in the universe. So there is a force of attraction between you and the pencil. But we're not really aware of this because we don't feel this force. The magnitude of this force is very, very small. But if you were to place yourself and the pencil in outer space and leave them undisturbed, over time, they would eventually move together. And this is because of Newton's law of universal gravitation, which states that there's a force of attraction between any two objects in the universe that have mass. So we're really familiar with gravity on Earth, and that's because the mass of the Earth is enormous. So we can't escape the force of gravity here on Earth. So let's take a look at Newton's law of universal gravitation. Newton's law of universal gravitation can be expressed with this equation. When we're talking about universal gravitation, we use the capital letter G as our subscript. When we're talking about gravity on Earth or on another celestial body, we use the lowercase g. So if we look at this equation, m1 is the mass of object 1, m2 is the mass of object 2, g is the universal gravitational constant, and it is 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared. And delta D is the distance between the two. So we're going to do an example using Newton's law of universal gravitation. And in this example, we're going to calculate the force of attraction between two individuals that are 1.5 meters apart. The mass of individual 1 is 65 kilograms, and the mass of the second individual is 45 kilograms. So we'll write down everything that's given. On your formula sheet, such as the one that you'll be using on your final exam, at the bottom you'll have a list of constants. And in this list, you will have Newton's universal constant. So we can use Newton's law of universal gravitation to solve this. Fg is equal to g m1 m2 over delta d squared. Be sure not to forget to square delta d. Let's sub and solve. Punch this into your calculator, and you get 8.6 times 10 to the power of negative 8 newtons. As you would have imagined, the force of attraction between two people sitting beside each other is really small. You shouldn't be able to feel it or sense it. And if we do the calculation, we can see that it's 8.6 times 10 to the power of negative 8 newtons. Now, just to be sure, let's take a look at our units and make sure that they end up being newtons. So we have kilogram times kilogram, which will be kilograms squared. And here, it's divided by kilogram, so these will cancel out. At the bottom, we'll end up with meters squared. And up top in the numerator, we have meters squared. So what we're left with is newtons. Now, I want to use Newton's law of universal gravitation, and I want one of the objects to be planet Earth. If we do so, what we'll be calculating is essentially what we have been calculating before, what the force of gravity that a celestial body exerts on an object is. So here's our example. We have a 60 kilogram person on Earth, and we want to determine the force of attraction between the object and planet Earth. Now, in the past, we just would have multiplied this by 9.8 to find the force of gravity. But we're going to use Newton's law of universal gravitation. The first thing we'll need is the mass of the Earth. Now, this is a constant value. This can be found in the appendix of any physics textbook. And its magnitude is 5.98 times 10 to the power of 24 kilograms. We know the mass of object 2 is the mass of this person, 65 kilograms. In order to solve this, we need our gravitational field constant, 6.67 times 10 to the power of negative 11 newtons times meters squared per kilogram squared. And we also need the distance in between these two objects. To do so, let's take a look at this diagram. The distance between the center of the Earth and the object is approximately equivalent to the radius of the Earth. The radius of the Earth is so big that the height of the person is irrelevant. It's negligible. So the distance between any object and the Earth is equivalent to the average value for the radius of the Earth. And this is another constant value. This can be found in the appendix of any physics textbook. And this value is 6.38 times 10 to the power of 6 meters. So we're going to use Newton's law of universal gravitation. That can be used for any two objects in the universe, even if one of the objects is a celestial body. So for this, we're going to put in this constant value, the universal gravitational constant, 6.67 times 10 to the power of negative 11. We're going to put in the mass of the Earth, which is 5.98 times 10 to the power of 24 kilograms. The mass of the person, 65 kilograms. And we're going to divide this by the radius of the Earth, 6.38 times 10 to the power of 6 meters, and we're going to square this. So I want you to imagine doing this for people of different masses. If you were to do this for a person with 65 kilograms, you'd punch this into your calculator. If you were then to change it for a person of 45 kilograms, you would still have to type in these three values again. I want you to do me a favor, and when you're doing this calculation, just compute this. Because every time you were to do an example with planet Earth, you would always have to put in the constant value of big G, the constant value of the mass of the Earth, and the constant value of the radius of the Earth. If you punch those three values in your calculator, what do you end up with? So we have 6.67 times 10 to the power of negative 11 times 5.98 times 10 to the power of 24 divided by 6.38 times 10 to the power of 6 squared. Good. We get 9.8. And the units would be newtons per kilogram. So all of those values, the universal gravitational constant, the mass of the celestial object, and the radius of the celestial object squared is how we get our gravitational field intensity. So in general, we can write this in a little bubble here. G, mass of the celestial object, over the radius of the celestial object squared will give you the value of little g. So Newton's law of universal gravitation can be used to calculate the force of gravity that a celestial body exerts on an object. But whenever we do the values for the force of gravity the celestial body uses or exerts on an object, we use the simplified version, which is force of gravity is equal to mg. In the next topic, we're going to look at the beautiful nature of physics. At the beginning of the course, we discussed 4 fundamental forces of the universe. We said there was gravity, electric force, strong nuclear force, and weak nuclear force. So today we're going to take a look at electrical force and the nature of this force. So electrical force is defined as the force of attraction between two charged particles or objects. I've drawn a large positively charged object. This large positively charged object has a deficiency of electrons, so has an overall positive charge. Its charge, we're going to say, is equal to Q1. And it is placed beside a smaller negatively charged object whose charge we'll say is Q2. And they're located at a distance from each other. So we know from grade 9 that the law of electrostatic attraction and repulsion states that these two objects should be attracted to each other. There should be a force that pulls them together. And there is a force. And the equation that governs this is one that looks like this. What should determine the force between the two? Well, it should depend on how much charge each object has. So it should depend on the charge of object 1 and the charge of object 2. Secondly, it should depend on how close they are together. The closer they are, the stronger the force of attraction. Whereas if these charged particles were far apart, the force of attraction would be smaller. So the relationship between the electric force of attraction is inversely proportional to the distance. So the farther they are, the less force, and the closer they are, the more force there is. If they are inversely proportionate, this expression would have delta D in the bottom. So we've almost completed the equation for electric force. This is what it looks like. K over delta D squared, where K is a constant, and it's equal to 9.0 times 10 to the power of 9 newtons times meters squared divided by coulombs squared. Now this equation in structure looks remarkably similar to the equation for universal gravitation. One deals with masses, while the other deals with charges. It's your responsibility to state the similarities and differences to not only these equations, but to the two forces, to Newton's law of universal gravitation and to electric force, both of which are fundamental forces of the universe. Good luck.